so much. Multiple pieces of evidence suggest most matter in our universe consists of an unknown component called dark matter. Studies of dark matter use multiple types of physics. And one type of physics that might potentially be relevant for dark matter studies is plasma physics. In this talk, we'll introduce plasma physics and discuss two different ways plasma physics might be relevant for dark matter searches. First, we'll discuss plasma instabilities and their relevance to dark matter studies. Then we'll discuss studies of pulsar radio emission and their relevance to Axion searches. So we'll start with an introduction to plasma physics. So charged particles exist in a plasma. Plasmas are ionized gases, which are composed of oppositely charged particles that are not bound to each other. On the left side of this slide, you can see a solid and a liquid gas sort of situation. And here on the right, you see a plasma. So you have oppositely charged particles, and they're not bound to each other. They're just moving around separately. So one of the distinguishing features of plasmas is that they have many particles. An example plasma that you might encounter is the one that's around the galactic center. At the Bondi radius, the density of this plasma is roughly 100 particles per centimeter cubed. And this is actually a very low density for a plasma, but it's already quite high. So you can see that large numbers of particles, like those in a plasma, need to be described by a kinetic description. And a lot of what plasma physics is the development of this kinetic description and the study of behaviors that exist in it. So the kinetic description of a plasma begins from particle trajectories. Each charged particle in a plasma has an orbit and position and velocity space. So in the upper left side of this slide, you see position space, and a given particle, which I label with a subscript I, has a particular orbit and position space. Then on the right side here, you see velocity space, and each particle in a plasma, which I can label with a subscript I, has an orbit and velocity space as well. To describe a plasma, we can write an exact distribution function that represents all particles of species S. So I can represent this with capital NS, and it's a function of position, velocity, and time. And this is given by a sum of the product of delta functions over the individual positions and velocities of particles in the plasma. These positions and velocities evolve with time according to electric and magnetic fields, because the particles in the plasma are charged. So you can see how the position is changing as a function in a way that's determined by the velocity. And then you can see how the velocity is changing in a way that's determined by the electric field and the magnetic field. And these electric and magnetic fields are total fields. So this includes fields that are externally imposed and fields that result from particles in the plasma. So the exact distribution and fields are far too complicated to use, because if you think about it, a plasma has a lot of different particles with a lot of different positions, a lot of different velocities, and each of these particles will produce electric and magnetic fields, and it's just way too complicated. So to study plasmas, we write plasma quantities as ensemble averages over different realizations of the same distribution plus fluctuations. So I can write my total distribution function and write it as an average distribution function over many different realizations of the same plasma, plus some fluctuations. I can take my overall electric field, write it as an average electric field over many different realizations, plus fluctuations. I can take my magnetic field, write it as an average magnetic field, plus fluctuations. And you can see what this looks like graphically for the electric field in the plot sketched on the bottom of the page. So if I have a plasma labeled by a coordinate x, I look at the electric field. Actually, the electric field is quite spiky because you have a lot of particles in the plasma and they're going to create local electric fields. But these spikes are just fluctuations, which would average out if you took many different realizations of the same plasma. And there's also an average electric field underneath it all, which is given by this E. So if we differentiate and apply equations of motion to the exact distribution function and write in terms of the average quantities from before, we can write a plasma kinetic equation. So this kinetic equation relates the distribution function of a particular species to the electric fields and the magnetic fields. And then there's a big term on the right, which represents contributions from fluctuations in the electric and magnetic fields and in the particle distribution function. These fluctuations are usually represented with a collision operator, which you see in the bottom of this slide. So we've derived a kinetic equation, which represents the distribution function of a species S, how it responds to electric and magnetic fields, and there's a role of a collision operator. So when people study plasma physics, a lot of what they do is study this equation and the behaviors that exist in it. So the kinetic equation suggests that there's a very important length scale in a plasma, and this is the Coulomb mean free path, which is the scale of binary collisions between particles. The collision operator's size can be represented by a thermal speed and a mean free path times the distribution function. So this mean free path can also be thought of in terms of a cross section. So the mean free path times the density times the cross section for collisions is about 1. So this is a very important length scale that characterizes plasmas you might encounter in nature. You can see a representation of collisions on the right side of this slide where particles are colliding roughly every mean free path. So the kinetic equation is a rigorous description of a plasma. As I said before, a lot of what plasma physicists do is study this equation and all the behaviors in it. And through doing this, they've determined that this equation is very, very complicated. It's really difficult to understand analytically. It's also very difficult to simulate numerically. So plasma physicists often study fluid quantities, that is the density, fluid velocity, and pressure, instead of the distribution function, because this is a lot more tractable. So plasmas are often studied with fluid treatments. On the right side of the slide, you see a simulation from one of the EHT papers. This is an MHD simulation. So they're trying to study a plasma, but studying the kinetic equation is way too complicated. So they're going to take a simplified fluid treatment, which is called an MHD treatment, and they're going to simulate that instead. This is very commonly done in plasma physics. So fluid quantities are moments of the distribution function. For a given species, the density, velocity, and pressure are defined as moments of the distribution function. So you can get the density of a species S by taking the distribution function of that species and integrating over velocity space. You can get the velocity of a species S by taking the distribution function of a species S, multiplying it by velocity, then integrating it over velocity space and defining it a velocity accordingly. And you can get the pressure of a species S by taking the distribution function of a species S, multiplying it by velocity minus the velocity of the fluid times velocity minus velocity of the fluid, and integrating over velocity space. So to understand how these fluid quantities evolve, plasma physicists take moments of the kinetic equation and apply two assumptions. They assume that the distribution rate of change is much slower than the collision rate. So they assume the partial time derivative is much slower than the thermal speed over the mean free path. And they assume that the distribution is constant over a mean free path. So things are not changing very quickly. With the previous statements, they can write a set of fluid equations, which describe how the density and the velocity of a plasma behave and how these quantities are related to the pressure as well. So with some additional steps, these equations can be used to derive the magnetohydrodynamic equations, which are sort of a special form of the fluid equations. That's an imprecise terminology, but you can think of it roughly as a special form of the fluid equations. So the intuition for describing plasmas as a fluid can be seen on the right side of this slide. So plasmas are, of course, a collection of particles that are always moving around and always colliding. But in a very highly collisional plasma, particles are colliding so often that they're staying really close to their neighbors. And groups of particles staying close together are like a fluid element. So this is a rough intuition for why you can describe plasmas as fluids. All right, so I've given you a rough 10-minute introduction to all of plasma physics. So now we're going to move on and describe how the physics that we've discussed previously can be relevant to dark matter searches. So we'll start by describing plasma instabilities and their relevance to dark matter. So it might be that dark matter is governed by equations like those that govern a plasma. I will note that dark matter collective interactions are very constrained, but nonetheless, it might be that dark matter is governed by equations like those that govern a plasma. If so, the dark matter might exhibit behaviors that plasmas exhibit. So they might exhibit behaviors that plasma physicists have discovered and learned about by studying the physics that we've discussed in the first part of this talk. A major type of plasma behavior is a plasma instability. So a plasma instability is represented very schematically by the diagram on the left side of the slide. So an instability exists in a plasma when a plasma is in a steady state, like this ball on top of the hill is. So if that ball is just there with no one touching it, it's fine, it's going to stay there. But if you gave it a little tap, it would very quickly roll down the hill because this ball is an unstable configuration. Likewise, many plasmas are in unstable configurations. So if you gave them a little tap, they would rapidly develop a special type of wave or other sort of structure in the plasma. And there are many, many different types of plasma instabilities. One very typical plasma instability is a tearing mode. So in this talk, we'll present a brief overview of this instability, and we'll discuss a little bit of the state-of-the-art research that is being conducted on this instability. And as we do this, we should bear in mind that if dark matter were governed by equations like those that govern a plasma, something similar could occur in dark matter. So this tearing instability is a plasma instability that occurs when oppositely directed magnetic field lines in a plasma are pushed together. In a fully ionized plasma, a reversing magnetic field forms a current sheet of width A, length L, alphane speed VAI naught. So the alphane speed is just a typical speed of the plasma, and resistivity eta. If the combination of these parameters that we call a Lundquist number, SL, is sufficiently large, the tearing instability will onset when a current sheet narrows. And after the tearing will initially onset with a linear stage, and it will eventually develop into a nonlinear stage called the plasmoid chain. So this instability behaves as you see schematically on the bottom of this slide. So if you have a plasma with a reversing magnetic field over a sufficiently large scale, this magnetic field will form a current sheet. You can see that you'll have current in the center of this magnetic field configuration. If this magnetic field is pushed together by flows in the plasma, the current sheet will get narrower and narrower. And once the current sheet is sufficiently narrow, you'll get an onset of an instability. So you'll get a structure arising in your magnetic field that looks schematically like you see in this red thing here. So this is not something that initially exists in the plasma, but it's a situation where if there's a tiny fluctuation, it'll grow up spontaneously. Just like that ball on the hill, if you gave it a little tap, it would roll down the hill. If this plasma gets a little tap, which it certainly will, it will develop this structure. This is a linear instability in the middle panel, but as it grows up, it will evolve into a nonlinear configuration, which is called a plasmoid chain. So this is represented by a structure in the magnetic field, which you see schematically in red on the right side of the slide. All right, so this instability was a very hot topic in plasma physics in the last decade. Many plasma works from the last decade studied the onset process. So they studied stage 1 and stage 2 of the process we showed schematically on the previous slide. I list some plasma works that studied this instability in the last decade at the bottom of this slide, but there is a very extensive literature. So these works all add a little bit of a different perspective to the story, but they have one rough consensus. And to arrive at this consensus, they've used a growth rate for the linear instability, which was derived in the last century by Firth, Copy, and some other plasma physicists. So this says that the growth rate of the linear tearing instability depends on the width of the current sheet A of t in the way that you see in the red box. So these works determined that tearing onsets when the linear growth rate, gamma, becomes larger than the formation rate, capital gamma. And the formation rate describes how quickly your current sheet is forming, how quickly your magnetic field lines are being pushed together. And this is usually modeled as constant. So the consensus of these works is shown schematically on the right side of this slide. So here I have a schematic diagram where along the x-axis I have time. And as time goes on, your magnetic field is getting pushed farther and farther together, and it's getting narrower and narrower. Along the y-axis, I have rate in arbitrary units. Throughout this whole process, the current sheet is forming at a constant rate, which is given in green. And as the current sheet gets narrower, the tendency to tear is getting higher and higher. The consensus of the works is that onset happens, which is the plasma becomes unstable, as you see in this diagram here, when the tearing growth rate is much larger than the formation rate. So this has been a really extensive discussion of plasma physics. There have also been other works in the last decade that examine the nonlinear stage of this instability. So this is the third stage that we saw in the initial description. This is the stage where you have a plasmoid chain that you see here. Again, I list several works that participated in this discussion, but it was very, very extensive discussion. These works observe a chain of plasmoids, which is with a distribution of sizes. So here I have a plot from one of the papers that studied this instability. The top panel shows the magnetic field, and the bottom panel shows the speed in the plasma, the speed directed along the current sheet, or the velocity directed along the current sheet. So you see that you have these structures in the magnetic field, which are called plasmoids. So this is the nonlinear stage of this instability. So plasma physicists discussed this instability quite a lot in the last decade, and they did a very comprehensive job of it. However, this discussion focused on standard MHD plasmas, and many plasmas include additional physics, which is not in standard MHD plasmas. For example, many plasmas are poorly ionized. So poorly ionized plasmas include a plasma with ionized particles and also a large number of neutral particles that are interacting with the plasma. So I give some examples of poorly ionized plasmas on the right side of this slide. An example poorly ionized plasma is a molecular cloud with an ionization fraction of 10 to the minus 4 to 10 to the minus 9. It's also the solar chromosphere, which can be fully ionized in some parts, but fairly poorly ionized in other parts. The diffuse ISM has an ionization fraction of 10 to the minus 4 to 1. And protoplanetary disks are extremely poorly ionized with an ionization fraction of roughly 10 to the minus 10. So these are really important plasmas, and they were totally neglected by the discussion in the last decade. So current plasma research considers how the instability can be modified by the new physics in these plasmas. So one recent study of this was one that I published in 2024, which studies the linear and nonlinear tearing instability in an MHD poorly ionized plasma. So this means that we studied this plasma using the fluid equations that I discussed in our lightning speed introduction to plasma physics. So we studied a neutral fluid and an ionized fluid, which were coupled by ion-neutral collisions, ionization, and recombination. And we did this with simulation and with analytics. So we were able to observe the onset of this instability and the growing of a plasmoid chain in our simulations. So I'll show the result of these simulations on the right side of the slide. So I'm going to show you a movie in this movie will show you current, which is normalized to appropriate parameters for this problem. And it's going to show you current in the current sheet, which is labeled by a coordinate x across the current sheet, also appropriately normalized, and a coordinate y along the current sheet. The parameters in the simulation are at the top of the slide if you're familiar with my paper and are curious what they are. But if you're not, you can ignore the gray box. And this movie will be labeled by time appropriately normalized. So what we're going to see here is we're going to see a formation of a current sheet. So here, magnetic field lines in the plasma are getting pushed together. And as a result, there is a formation of a current sheet, this growing current. At a certain point, this situation will go unstable. And you'll see the formation of a plasmoid chain. So somewhere in here, there's a linear tearing instability, which is so quick we can't see it. And then we get into the nonlinear stage. So I'll play this through one more time. So this is an example of a very typical plasma instability that's been widely studied, but this paper was the first to study it in this way in poorly ionized plasmas. This work identified several differences from fully ionized tearing. In particular, onset in poorly ionized plasmas occurs only after the current sheet is fully formed and the formation rate is 0. This was a really interesting piece of physics, which you can read about in the paper if you're curious. And we also recognize that poorly ionized plasmoids were sites of enhanced ionization fraction. So a poorly ionized plasma has a big ionized species, which is the plasma, and then you've got a big neutral species, which is hanging out there interacting with it. And the ratio between the ionized density and the neutral density is the ionization fraction. You can plot this on the top of the slide in the nonlinear stage of the tearing instability. You can see that the ionization fraction is much higher in these little patches, which correspond to the plasmoids. So this was a really interesting effect. So we've just discussed a very typical plasma instability and recent research that has been conducted on it. If the dark sector has collective interactions like those that exist in a plasma, so again, these are very constrained, but if they exist, these instabilities could be a mechanism for structure formation in the dark sector. Plasma instabilities could also heat dark matter, and both effects could have observable consequences. So studying plasma instabilities can help us to understand these consequences. All right. So we've discussed the first way that plasma physics is relevant to dark matter studies. Now we'll discuss another way plasma is relevant to dark matter searches. And this is the application of plasma physics to axion searches. So one very strong and at the moment quite popular candidate for dark matter is a particle called the axion. The axion is very well motivated because it could potentially solve a problem in particle physics. The diagrams on the right schematically represent this problem in particle physics. We won't go into that in detail, but I think the non-trivial fraction of this room is probably familiar with it. So the problem represented by these diagrams would be fixed if you have an axion. And this is a problem that exists initially independently of the dark matter situation. But it's also possible that the axion could be dark matter. So this is very exciting. So axions can be produced in multiple ways, but one of them is by a strong fluctuating electric field, which is parallel to a strong magnetic field. This mechanism is represented by the following equation, governing the field A of axions of mass Ma and coupling constant Ga gamma. So this equation is given in the gray box. It relates the time derivative of the axion field to a spatial derivative, the axion mass, the axion field, you've got a coupling constant, and you've got electric and magnetic fields. So you can see that these red terms could potentially source axions. In addition, axions would create a slight modification to Maxwell's equations. In a system with axions of mass ma, momentum h bar ka, and density na, you could take your standard Gauss's law and Ampere-Maxwell law would not look like you expect them to. So in this gray box, I have our familiar Gauss's law and Ampere-Maxwell law. But if axions exist, these would be modified. In particular, they would get new terms, which you see in red and purple here. So Gauss's law would get a contribution that depends on the coupling constant, the magnetic field, and the axion field. The Ampere-Maxwell law would get contributions which depend on the coupling constant, the axion field, the magnetic field, the electric field, and the axion field. And here I've written an expression for the axion field, which depends on axion density, axion mass, axion momenta, axion frequency, which depends on axion mass, and axion momentum. So one way that physicists look for this axion particle, which is a potential dark matter candidate, is by looking for this change in Maxwell's equations. And this change might subtly affect the behavior of waves and plasmas, because we discussed at the beginning of this talk that plasmas are this state of matter. We've got all these charged particles, which are interacting via Maxwell's equations. And if Maxwell's equations are different, then the behavior of plasmas are different as well. So this is actually a really interesting area of plasma physics. But a big problem is that we don't have any idea, or it's not clear what the value of the coupling constant and the axion mass would be in this modification. So if we look at the potential phase space of potential axion coupling constants and masses, you see it on the right side of this slide. So along the x-axis, I have axion masses. Along the y-axis, I have a coupling constant. This yellow band is a particularly well-motivated type of axion. But axion-like particles could have masses and coupling constants that are outside of this yellow band. And you see various experimental constraints that have ruled out certain areas of this phase space. Although it's not clear what parameters would describe an axion, some theories describing how axions would be produced suggest that a frequency in the radio range is most likely if the axion is dark matter. So they suggest maybe we should start looking for axions by looking at frequencies of several gigahertz. So with this red line here. All right. So unfortunately, detecting this particle on Earth is very challenging. In Maxwell's equations, axions provide an effective current density, which is determined by the coupling constant, the axion field, and the magnetic field. And unfortunately, magnetic fields and axion densities on Earth are very small. So the strongest magnetic field we can make on Earth is roughly 45 Tesla, and you're not going to be able to use that reliably in an axion experiment. So if you want a magnetic field you can reliably use an experiment, it's going to be about 14 Tesla. And the density of axions on Earth is roughly 0.3 GeV per centimeter cubed. So this means that the effective current density caused by axions on Earth would be very small. So at well-motivated parameters, it might be 10 to the minus 18 amp. So its typical cell phone charger is roughly 1 amp. So this is a really minuscule signal. And in addition to the signal being very small, we don't know exactly how small it would be, and we don't know what frequency it would be at. So it's very hard to look for this signal, but nonetheless, many experimentalists worldwide are trying to do it. So detection of axions would be much easier with a stronger magnetic field and much larger axion density. One location with these characteristics is a pulsar. A pulsar is a rapidly rotating magnetized neutron star which is surrounded by plasma. You can see an artist's depiction of a pulsar on the left side of this slide. So you see the neutron star in orange. You see the magnetic field around it in blue. And you see some emission coming from the pulsar in purple here. So this pulsar is surrounded by a plasma. And there's speculation that the pulsar might also be surrounded by a cloud of axions, which are created by fluctuating electric and magnetic fields in its magnetosphere. So this means that the parameters for axion detection might be a lot better around a pulsar. So I repeat our parameters from a terrestrial laboratory on the left side of this slide. So we've got a magnetic field of 14 Tesla, which, if you live on Earth, is really strong. And you've got an axion density that you see here. But if we go to a pulsar, the magnetic field might be 10 to the 8 Tesla. So that's really a lot more than 14 Tesla. In addition, the axion density could be as much as 10 to the 22 times higher. Although, obviously, the axion density is highly uncertain. So this means that if you want to look for axions, it's probably a lot easier to do it in a pulsar than on Earth. And in addition to this, pulsars produce a large amount of radio emission, predominantly from the polar region. You see this emission represented schematically in this artist's depiction with the light purple glow here. Because theory suggests an axion frequent field might oscillate at radio frequency, it is possible that very subtle effects from axions exist in this radiation. So maybe we can study pulsar radio emission, and by looking for these subtle effects from axions, we can determine the coupling constant and the mass of the axion, and use these to guide experimental searches on Earth. This would be a really great idea. Unfortunately, there's a major problem with this idea. And the problem is that pulsar radio emission is difficult to understand. We see all this emission coming from pulsars, but we don't really understand how it's produced or what information we can get from it. In fact, until recently, we didn't even understand why this emission was as bright as it was. So if you look at the total brightness of the radio emission from a pulsar, you see that it has a luminosity of roughly 10 to the 27 to 10 to the 31st ergs per second. You see some observations of this luminosity on the left side of this slide, where along the y-axis you have radio luminosity, and along the x-axis you have the period of the pulsar that was being observed. And you can see that these pulsars have a wide variety of luminosities, but they all roughly fall in this range. So until very recently, we had no idea why radio emission from a pulsar was this bright. So if the overall luminosity is not explained, understanding of pulsar radio emission is really not good enough to look for axions. We'd like to be able to look at these pulsars, say, ooh, that's a spectral feature from an axion. Experimentalist, go study these parameters here on Earth. But we can't do that because we don't understand pulsar radio emission at all. So this is where plasma physics comes in to axion searches. So astrophysicists are not able to fully understand radio emission coming from pulsars, but radio waves are much better understood by physicists working on laboratory plasma experiments. So one example of a laboratory plasma experiment is a tokamak, which could produce energy from fusion. On the left side of this slide, you see a tokamak experiment. So there's a lot of equipment around it, and then at the center, you have a plasma here. And the idea is this plasma might create energy. To work effectively, this experimental plasma has to be really hot. And high temperatures in this plasma are routinely obtained by launching radio frequency waves into a plasma, which interact with plasma particles and resonantly heat them. So this is a photo of the inside of a plasma experiment, of a tokamak in particular. And you can see that around this plasma experiment are a bunch of antennas. These antennas are used to launch radio waves into the plasma, which then heat the plasma. And the study of these waves and their use to operate plasma experiments here on Earth is extremely routine. Plasma physicists are really experts in this. So lab plasma physicists understand radio waves using well-developed mathematical techniques. They take Maxwell's equations, they take a kinetic equation, like the kinetic equations we presented at the beginning of this talk. They take charge and current density definitions, And they take a large set of well-developed mathematical techniques, and they have a deep, experimentally validated understanding of radio waves that results. So these techniques that are well established in plasma physics can be applied to understanding pulsar emission and potential Axion effects. So in this final section of the talk, we'll begin by discussing how these techniques were applied to understanding pulsar radioluminosity, and then we'll discuss how this work has helped with Axion searches. All right. So efforts to understand radio emission focus on physics occurring in the polar region where radio emission is produced. So they focus on the region that's called out with this yellow arrow here. This region has a strong inductive electric field, which creates a complicated pair discharge. So what's actually going on in this physical system is very complicated, and the point of this diagram is just that it's complicated. You don't have to understand the diagram any further than that. But for the purposes of this talk, we're going to radically simplify what goes on. So I'm going to take the neutron star situation here and draw a schematic diagram of it, where you have the neutron star surface in orange, we've got the magnetic field in blue, we've got the electric field. So this electric field will accelerate electrons from the surface to a very high Lorentz factor of roughly 10 to the 7. I have the definition of Lorentz factor here in purple. These electrons will curvature radiate gamma rays, which is seen in yellow here. And these gamma rays will be absorbed in the magnetic field, and a QED process will continually create lower energy pairs. So these lower energy pairs will be very strongly affected by the electric field, and they'll attempt to screen it. So depending on the sign of charge in the pair will either get dramatically accelerated in one direction or it'll get turned around. And this process will attempt to screen out the electric field, and it will overshoot, and it will set up waves that are damped by more pairs. So these damped waves might become radio emission, which leaves the plasma, schematically shown in this green arrow. And this process repeats after the plasma leaves the polar cap. So you'd have this continual formation of plasma waves, and then it would clear out, and then it would start again, and you'd see radio emission on Earth. To understand the basic physics of radio emission, I modeled the cascade evolution by the screening and the damping of the vacuum electric field by continuously created pairs. So I took our simplified situation and made it even simpler. So I had an electric field, and I injected pairs that represent pairs created by the QED process, and saw how those pairs fed back on the electric field. And this oscillating electric field represents the plasma waves in the polar cap, which would escape as radio emission. So the screening and damping of this field is shown at right in a PIC simulation. So a PIC simulation is basically a plasma physics simulation. You don't need to understand any more about it than that. So here I have normalized time on the x-axis, and I have the strength of the electric field on the y-axis. So I have a really strong electric field initially. And this electric field initially exists in vacuum. So if I look at the density of the plasma, it's initially 0. And then as I add more pairs into it, the pair density increases. In response to the increasing pair density, the electric field is initially sent to 0, and then it starts to oscillate in a way that produces plasma waves. So our work built analytical models of a screening and damping process and compared them to the simulation using laboratory techniques. And we were able to explain the luminosity by doing this. So we identified 2 phases in the evolution of the electric field, which exists in the pulsar polar cap and produces radio emission. So the first phase is nonlinear. So if we look at the electric field evolution, where we have time on the x-axis, electric field strength on the y-axis, initially we have very strong waves that are damped very strongly. So in this stage, newly added pairs are fully reversed by the electric field, so they get turned around. Then there's a second stage where newly added pairs are not reversed by the electric field, and the electric field is not very damped. All right. So we're a little short on time. So I'm going to skip one slide. And all right, so if we look at the evolution of the electric field, we see that its strength decreases very strongly, and then it stops decreasing. So this electric field represents the plasma waves that exist in the polar cap of the pulsar and that escape as radio emission that we see. So the amplitude of the radio emission is roughly described by the strength of the electric field waves when they stop damping strongly. So this point here really roughly represents how strong the emission that we see is. So this amplitude is set by the point at which the pairs can no longer be fully reversed. So we can develop a plasma physics condition that represents how much the pairs can be turned around and relates them to how quickly they're injected. And with typical parameters, we can work out a strength of the emission that escapes the polar cap. And we can compare this to the observed radioluminosity and get a value which is consistent with the observed luminosity. So what we've done here is we've applied plasma physics to the study of pulsar radio emission, and we've developed an explanation for the radioluminosity. So this work uses plasma physics to build confidence that we can understand pulsar radio emission. And the conceptual advances in this work have helped in Axion searches. One search used a model of oscillations from this paper to understand how axions might be produced in polar cap discharges and how these axions might lead to emission. Another paper used the model for oscillations to understand the momenta of the created axions in this process. So we've covered a tremendous amount of ground in this talk, so I'll just very briefly wrap up. So we began by discussing how plasmas are ionized gases described by kinetic and fluid equations, and we really quickly outlined how those equations are derived. Now we've discussed two different ways that this physics can be relevant to dark matter searches. The first way is that plasma instabilities might occur in a dark sector. They also might not. And these plasma instabilities are a really rich area of research in the plasma physics field. I gave you an overview of one instability and what the most recent work on that instability is. Then we've discussed the second way that plasma physics is relevant to dark matter searches. And this is that axions might be produced in pulsar plasmas and might influence emission from those plasmas. To understand this emission, which might one day set the stage for understanding the effects that axions could have on this emission, we can use techniques that are well developed in plasma physics and apply them to this emission. So thank you very much for your attention, and I'm happy to take questions.
Okay, thank you, Libby, for the great talk. We have maybe 3 minutes for questions. Diego and then Melissa.
Yes, related to, thanks for the talk, very nice. Yeah. I'm always failing. Can you hear me better?
Yeah, I can hear you.
Good. So, related to the first point, so you have in mind dark matter with two different charges and some dark QED, saying, I imagine.
Right. I've not worked in this area, but my understanding is this is what people do when they
So
apply, yeah.
one difference I see is that the waves that you showed are very quickly damped, no, on large scales.
So that's not actually true for the waves that I showed. But
In the picture, it seems that from your picture, it seems that they were not propagating at large distances, or not?
I mean
this would depend on the
plasmoid
viscosity.
structures, and they fly out. They don't go away.
Yeah, no, but not in the
leave in
transfer
stimulation
direction.
domain. Yeah.
So in one direction they propagate on long distances, and in the transverse no, or like.
Right. So basically, what's happening there is you have a magnetic field that has one orientation, and these instabilities sort of exist between the magnetic fields. So they're sort of you push the magnetic field together, and this like bubbles up between the magnetic field, and they get pushed out.
Okay, but when like the support of these waves is relies on the fact that there is a large scale magnetic field.
Oh yeah, for sure.
Okay.
Yeah. otherwise, you just fling these things out and they sort of get lost.
They are damped by the viscosity
they
of the
eventually
plasma.
collide with other things and they eventually go away. Yeah.
Yeah. So the difference with dark matter that I see is that dark matter doesn't dump much oscillation. So maybe this can even have more catastrophic.
Yeah, for
effects.
sure. For sure.
Because
just to make sure I understand, would these plasmoids emerge if there's no external magnetic field? Like just the one produced by the plasma, could that do anything? Could that give you these instabilities?
So this magnetic field exists in the plasma. I don't think it's really appropriate to think of it as an externally applied field. But if that magnetic field did not exist, you would not get these plasmoids.
But like a plasma could generate like its own magnetic field?
Yeah, for sure. It could generate its own magnetic field, and then you could get the development of this instability.
Yeah, and I guess maybe just if you could help me a little bit with like a physical intuition of like what's happening in those plasmoids and like how you would be able to see them.
Yeah, so I'm not sure the best physical intuition to give. It's just that energetically, that configuration of the magnetic field is more favorable for the plasma, so it tries to go to that. But you can think of them almost as little bubbles of plasma, so it's sort of like wrapped up in a magnetic field, and they're moving around like that. What was the second part of your question?
Oh, just like how we'd be able to look for those, or like how you can see evidence of them being there.
Great. So one way you could look for these is, so for instance, in a poorly ionized plasma, these correspond to a much higher ionization fraction. So you could measure ionization fraction in various parts of the plasma, and you could call out these plasmoids by seeing that ionization fraction. There's also ways of measuring the magnetic field structure in a plasma by like shooting various things through it, and that's another way that people try to diagnose these structures.
Yeah, Marco?
So I have a question. Is there like, since I guess they are in some sense some collective effects, is there some quasi-particle description of plasmoids or other excitations in plasma? Like similar to what condensed matter people call holes,
I think that people have advanced these methods. They're not really mainstream, I would say.
Okay.
But I think they have been done.
Okay, thanks.